Today we will start off on a new topic and that is namely weak nonlinearities. In electronic circuits. Right. So far we have basically spent most of the semester on talking about circuits that are linear, right. First we talked about circuits which are both linear and time invariant. Then we talked about circuits that are linear, but varying in time, and specifically those that vary periodically with time, right. But in reality it turns out that most circuits are essentially nonlinear, and with a lot of design effort they still turn out to be within quotes nonlinear, but the nonlinearity is very small. The hope is that the nonlinearity is sufficiently small that it can be ignored, right. But in many cases, even this weak nonlinearity causes problems, and so today we are going to start studying about weak nonlinearities in circuits, and for the time being we will stick to circuits that are supposedly linear and time invariant, okay, and we will try to understand what nonlinearities do to circuits, right. So, let me take a simple example. Let us say you have an amplifier here, and ideally we want this amplifier to be linear. So, V out is supposed to be some gain A0 times Vi, right. In practice, however, there is going to be A1 Vi square plus A2 Vi, sorry, let me make this A1 Vi plus you will have A2 Vi square plus A3 Vi cube and so on, right. So, this is the within quotes linear term, and these are all nonlinear terms. Now, let us see what it means to say weakly nonlinear. So, when you say weakly nonlinear terms, it basically means that this A2 Vi square plus A3 Vi cube, etcetera, the sum of all these is much smaller than the linear term, which is A1 Vi. Right. And in most work, I mean, unless you want the circuit to be deliberately nonlinear, in most linear most circuit design techniques basically will try to ensure that the strength of the nonlinear terms is very small compared to the strength of the linear term. There are, of course, there are deliberately nonlinear circuits where the nonlinearity is needed for the circuit to function, but at this point we are not concerned about such circuits. What we are more interested in is, well, the circuit was supposed to be linear. Now, there are some small nonlinear terms. What happens to the output, right? And we will start with the simplest things first. I mean, I am sure you have seen this in some context or the other. And because the nonlinear terms are very small, typically it is only these terms which are dominant sources of nonlinearity. and the higher order terms are ignored. Okay, at least for hand analysis. Well, in and if you have a computer, of course, you know, you can take as many terms as you want. Now, the first manifestation of nonlinearity is that it creates tones which should otherwise not be around. So, let us say V out is A1 Vi plus A2 Vi square, right. All the higher order terms are either too small or non-existent, or can be so small that they can be neglected, and A2 Vi square turns out to be much smaller than A1 Vi. Okay. And the question is, what happens when Vi is a sine wave with amplitude capital A and then cos say 2 pi ft, right. So, V out therefore is A1 A cos 2 pi ft, that is simply the linear term, plus A2 A square cos square 2 pi ft, and recall that 2 cos square theta minus 1 is cos 2 theta, and therefore, this is nothing but A1 A cos 2 pi ft plus A2 times A square by 2 times 1 plus cos 4 pi ft, all right, which therefore can be seen to be A2 A square by 2 plus A1 A cos 2 pi ft plus A2 A square by 2 cos 4 pi ft. Okay. And so, as a consequence of nonlinearity, we see that when you have second order nonlinearity, you see a DC offset, even though the input was, the input is basically you know, clean, right. It's a sinusoid with 0 average value. However, when it passes through an even order nonlinearity, right, you basically start to see DC offset, and the intuition is the following. The ideal linear output should have been, the linear characteristic would have been that. So, this is V I and this is V out. If there is nonlinearity, what happens? Well, you probably get a curve, say I do not know, perhaps like that. Okay. So, so even though the input is a sinusoid whose average value is 0, yeah, I mean, which basically means that the input spends equal amount of time on the right as well as on the left, right. Clearly, you can see that when the input is on the right, the output is always it's basically its output is always larger, right. And likewise, when the input is negative, the output is always larger than the linear output, right. So, since whether the input is positive or negative, you are always getting a value higher than what you put in, basically means that there is DC offset. right. Then of course, this is the linear term, there is no surprises there, right, and this is the second harmonic distortion, right. So, in other words, we put in an input frequency of f, but our output frequencies are 0, f and 2f. Okay. And anyway, well, you might argue that even in a linear periodically time varying system, you get an output frequency which is different from the input frequency, but there the output frequencies are f plus fs, f plus 2fs and so on, and not f and 2f and 3f and so on, right. So, the next thing is how do you quantify how linear or nonlinear the amplifier is. So, one way to do that is to calculate what is called the second order harmonic distortion. Right, which is the ratio of this strength of the second harmonic to the ratio of the fundamental at the output. Okay. And this is as you can see, this is A2 A divided by 2A1, right, and in dB this is simply 20 log to the base 10 in dB. All right. Another thing I like to draw your attention to is the strength of the second harmonic. See that notice that the strength of the second harmonic is proportional to a square, right. So, in other words, if you double the input amplitude, let us say it goes up by a factor of 2, which is 6 dB. What comment can you make about the amplitude of second harmonic? Yeah, that becomes a square. So, it goes up by a factor of 4, and that is goes up by a factor of 4, which is 12 dB, right. So, in other words, in general, for every 1 dB increase in input leads to 2 dB increase in second harmonic amplitude. Okay. And why does it make intuitive sense that the second harmonic strength is proportional to a square?
Squaring it is related.
Yeah. So, basically, Yeah. So, the distortion terms are basically coming in because of the V I square, which is V I multiplied with itself. So, if you increase the input amplitude, right, and you obviously multiply it with itself, then you basically get a squared effect. Okay. And so, okay. So, this is also equivalent to saying that if you increase the input amplitude by 1 dB, what comment can you make about HD2?
But HD2 will be 1 dB also.
HD2 will also increase by 1 dB.